All right, so I'm going to introduce you guys, whoops, sorry. I'm going to introduce you guys to some terms today. We're going to talk about some different notations that we use to measure angles, difference between scalars and vectors. We briefly talked about the difference between some scalars and some vectors when we talked about calculus. And then we'll talk about different ways that we can represent vectors as well. Okay, so I think some of us maybe already know what is a scalar versus what is a vector. Does anyone have that information for us? Marcos, thanks for volunteering. What's a scalar versus a vector?
A vector is based on two scalars and it has a direction, while a vector is just like a quantity.
Okay, so a scalar is, yes, a quantity. And it's going to describe magnitude or size only. Okay, it can have units or it can have not. It can have not, or it cannot. Okay, and the important part of this is that it does not include a direction. Okay, a vector is also a quantity, but it has magnitude and direction. Okay, so the biggest difference is vector has direction as well as a magnitude, whereas your scalar does not have direction, it just has a magnitude. So there's a couple in this little chart, sorry, it printed out really small, but there's a couple examples of vectors and scalars in the chart here. I just kind of clipped it from the textbook. It's on page 304 of your textbook if you want to check it out. So as far as scalars, you'll see some examples of scalars on the left there. So like regular numbers are scalars. Temperature is a scalar. Area, distance, speed, and mass are scalars. And then we've got three examples of vectors, which would be displacement. An example of displacement would be excuse me, sorry, 1 centimeter at an angle of blank, whatever. So the 1 centimeter is your magnitude, and then of course your angle showing the direction gives you that element of the vector. Or even it could be like 5.3 kilometers north, right? So that gives us a specific direction in which that's going. Whereas when we talk about distance, we're just talking about they traveled 5.3 kilometers, no distance, no direction in that. And then velocity is similar to speed, but we have, again, a direction with that. And then force also has a direction as well, so 10 newtons downward. Did everybody get these definitions on the top? Can I scroll? We're good? Okay. Let's scroll down. Okay, so I want you guys to see here, I just have to zoom out tiniest bit. I want you to see if you can decide whether these things are vectors and scalars. I'm going to give you a couple of seconds. You can just do V or S if you'd like. Okay. A. Car traveling 50 kilometers per hour east. This is a vector, yes, it has that direction. A child pulling a wagon with a force of 100 newtons at 30 degrees to the horizontal. Vector. C, man's mass of 88 kilograms. Scalar. A woman skiing at a speed of 25 kilometers per hour.
Scalar.
Lovely. Parachutist falling at 20 kilometers per hour. Vector. Acceleration due to gravity. Sorry, this should be squared. This is a vector for sure. The number 5, scalar. Your weight on a bathroom scale.
Vector.
This is a tricky one. This one's actually a vector, and weight is actually force due to gravity. Okay?
The golden force.
It's okay. Mark, yes.
When you have like kilometers per hour, like the unit per unit, wouldn't
Yep.
it normally be a vector?
No, that can be, so that's the difference between speed and velocity, right? Speed doesn't have a direction with it, but it still can be kilometers per hour or something like that. But vector has the direction with it. Yeah. Yeah. Yeah, that one is a little bit of a tricky one too. We consider falling to be downward.
Mark, the last question, it's like the grade 11 physics is the weight in the elevator question. It's like, are you heavier or lighter on a scale in an elevator?
Oh yeah, if it's going up or down. If it's going down, you're lighter. If it's going
Yeah.
up, you're heavier.
Question? No? Okay, moving forward.
So it takes away. Less normal force. Going down.
Yeah.
Yeah.
Okay,
Going up and down.
are we ready? Just waiting. Good? Okay. So there's different ways that we can represent vectors. One of them could be in words. So we've had a few examples in our lesson already today. But let's just say we say 5 kilometers traveled at an angle of 30 degrees to the horizontal. Okay, so we've seen quite a few of these already, so this would be like your idea of displacement. In a diagram as a vector that shows magnitude and direction. So specifically here, I would actually be creating a scale. So if I wanted to say this same example, but show it in an actual diagram, I would be creating a scale. Maybe that 1 centimeter is equivalent on our scale here to 1 kilometer. And then I would actually be doing my best to find the horizontal. So with my ruler, I would be doing 5 centimeters at approximately an angle of 30 degrees, which is why I want to make sure that within the next few days, everyone has a ruler and a protractor so that they can draw like 2 scale diagrams. And then this would be 5 kilometers. Okay, yeah.
That actually reminds me, for the first question on the thing yesterday, like, are we going to have to do these scale things?
Yeah. Okay. So in your diagram, this would be 5 centimeters. Okay, based on the scale that we developed here. Or maybe you can even say like 2 centimeters is equivalent to 1 kilometer if you want it to be smaller. Like if you can't fit 5 centimeters. Okay. All right, so we also use a notation to represent vectors, and that is we have the 2 elements to this, and then we show a little arrow on top. So I know that this is small, but it's actually like an arrow like this. And essentially A is going to be the tail of our vector, or it will be what we call like the starting point of the vector. And B is going to be the head of our vector, sometimes also called the tip of the vector, okay? So how we would write this would basically be, this is A, and this is B. Okay, we also sometimes represent vectors as a single letter vector. So it doesn't give you information about like the tail or the tip of the vector, but it just basically names that vector vector V. and it will be labeled like such. Do you guys use this notation in physics? No? So that will be new for you guys. Can I scroll? Okay. Okay. The magnitude or size of the vector is designated using absolute value brackets. Okay, so this means that the magnitude of vector AB, like I showed you above, or single letter vector V, we can actually write, does anyone remember what the absolute value sign is? Yeah, so it's like absolute value of AB, but in this case it actually means magnitude of AB and magnitude of vector V. Okay, so we so far have different ways that we can express vectors or write vectors. We know magnitude is if we see the two absolute value bars, that means magnitude of the vector. We also have different ways that we can write the direction of the vector as well. So one of the ways that we can write the direction of a vector is moving counterclockwise from the horizontal. So if I have something from the horizontal, I can kind of show that it's rotating counterclockwise. Okay, we have a measurement called true bearing, which is, oh, yeah, sorry.
So like for the first one, like the magnitude of the vector, if it's like written like that, so like let's say like the magnitude is like 10.
Yep.
So it would be like that equals 10. Like,
Yep.
oh,
Yep, or it's a notation that we use if we're like finding it or whatever. Yep. So from the horizontal, we'll rotate counterclockwise. We're very used to doing this in like when we were using like the cast rule grid. We started at the 0 horizontal and then worked our way counterclockwise from there. True bearing is measured from the north. So if this is our kind of like quadrant grid here, we have north, south, east, west. Oh, I put south on west. West, we actually measure from the north line and then measure clockwise. So if I wanted to write a vector here, or the direction of a vector, let's say I wanted, I don't know, 45 degrees, I would be measuring from here, and it would be the notation 0, 4, 5. So the 0 part in front is there for angles that are 2 digits or less. Once we get to 100, it's just 100 degrees. And the question would have to indicate to you, like, it will probably say true bearing or quadrant bearing, like within that question there. But for the quadrant bearing, you're actually going to see 2 directions there. So if you don't see like northeast or whatever, or southeast or whatever, then you can kind of assume that you were working with true bearing. Yep.
So the bearing is always north?
Yes, starting from north, measuring clockwise. Okay, and then quadrant bearing is always going to be between 0 and 90. And we usually measure from the south or north line, and then we measure toward the east or toward the west. So if I wanted to measure north 23 degrees west, we would have our quadrant grid. You're gonna have to make sure you know your directions, of course, for this. Never eat sour watermelons. And then we're gonna measure toward the west, 23 degrees from north. So I'm gonna start at the north line, and I will rotate 23 degrees toward the west. What was yours?
Never ending water.
True.
Sound of watermelon.
Okay, questions so far? Okay, so true bearing, we're measuring from the north line, always clockwise. Quadrant bearing, we're measuring usually from the north and south line toward the west or toward the east. Okay, so let's see some examples here. So we're going to describe each vector in words as best we can. And we're going to use either above the horizontal, we'll say true bearing, or we will use north blank west, or north blank east, or south blank east, south blank west, that kind of idea. So can somebody describe part A in words for us? So I need to tell about the magnitude of that vector, and I need to tell about the direction of that vector. So firstly, what's the magnitude? 14 centimeters. And how is this being measured? Is it being measured in true bearing, quadrant bearing, or from the horizontal? So we would say at an angle. So if you see this horizontal being measured and then counterclockwise, that's from the horizontal. So at an angle of 110 degrees from the horizontal, we would want to say. Lauren?
So it's not quadrant bearing?
No, you will see the quadrants, like you're going to see it like this if it's quadrant or true bearing. Yeah. Okay, part B. I have 2.3 kilometers. Can someone help us out with direction? Yep. What's direction for part B? It's true bearing, so we would say at a, we can either say at a bearing or at a true bearing of 135 degrees. If you just see at a bearing of 135 degrees, because we don't have the north and south in that, we kind of assume that it is true bearing. Am I okay to scroll down? Yeah, okay. So we would actually normally just say at a bearing of 135 degrees. So when we see bearing, we're going to assume it's true bearing. Okay, and this guy here, 9.8 newtons, how would I say this?
South 35 degrees west.
Yes, good. So we would say at quadrant bearing. I don't think it's necessary for us to say quadrant bearing, but I think in the textbook sometimes they do specify that it is a quadrant bearing, but it should be south 35 degrees west. Lewis?
How we know which side 135 degrees to, like, it's also probably to the other side.
Sorry, I'm not sure what you're asking me.
Like for 135, we can also do move it to the second part.
So this one, for true bearing, it's always measured from the north line clockwise. Okay, from the horizontal, we're measuring counterclockwise. So for part A, we're measuring from the horizontal, and then we always go counterclockwise from that one. Okay? Okay. So those are our 3 notations for direction. Okay, so we are going to, hopefully you guys have a ruler that you can maybe use. If not, you can do your best to create a scale ratio. Of course, I can't measure on here, so I'm going to do my best to create a scale. We are going to look at our different types of bearings, and then also create a scale here that we can use to draw our vector. So for instance, for the first one, maybe I can make 1 centimeter equivalent to 1 kilometer. And then you're going to have something that is probably, it's 20 degrees from the north line. So that's probably going to look something like this. And then we're going to label it with its name. And we're going to say vector v equals 2 kilometers. Yep, you can do that too. So if you want it, yeah, you can make 1 centimeter 2 kilometers and then just draw a line that's 1 centimeter. I think for the second one, because we have to do 4 kilometers, you could even do something like 1 millimeter is equivalent to 1 kilometer. And then you can just draw something that's 4 millimeters. So for this one, again, because you don't see any north and south and west and east, we're assuming that when we see bearing that it's actually true bearing. So we want to measure from this north line all the way around to 295. So it's going to be something like this is 270 measured from the north line. So it's going to be something that's like probably around here. Actually, maybe even a little bit less, something like this. And you should be kind of showing that as your angle there. That's the direction. And then we want to label this as vector u. That was a bad u. Vector u equaling 4 kilometers. And then you can label the angle as 295. Because it's called u in part B. It's the name of the vector. Olivia?
So when it's true bearings, it's always counterclockwise?
Yes. No, true bearing is clockwise. From the horizontal is counterclockwise. Okay, 30 kilometers per hour. Does anybody have a suggestion for scale that we can use for this? You're cheating. You're just making everything equal to. Yeah, you can do that, or
Centimeters equal to 15
maybe you can do like 10 kilometers per hour or something like that.
That's thinking, of course.
Or you can make it 30 if you want. That works. We'll make it 30 if that makes you happy. Okay, so we want to measure from the north line toward the east, 40, an angle of 40. And then we're going to make sure that this is 1 centimeter long. And we'll have w, vector w equals 30 kilometers per hour. Okay, and then last one here. Sure, you can make 1 centimeter equal to 40 kilometers per hour. And then our direction here is from the south line toward the west, 70. So it's going to be somewhere over here. Oops. And we're going to make it 1 centimeter long. And we're going to label it vector x. And we will say 40 kilometers per hour. Okay, you could have also done like 1 centimeter equals 20 kilometers per hour, and then you would have had 2 centimeters long. Okay, so you guys are going to try your best to make sure that you have a ruler and a protractor so that you can get some of these angles and scale drawings as close as you can to your scale. Any questions for this so far? Can I scroll? Okay, the last one is switching between quadrant bearing and true bearing. So we're going to write a true bearing of 150 degrees as a quadrant bearing. So sometimes it can be helpful just to draw a picture of what's happening here. When I'm measuring true bearing, I'm measuring from the north and then I'm going clockwise. So this is 90. 150 has to be somewhere around here. Okay, so we're going to choose the closest north or south line, which in this case the south line is actually much closer for us to do. And then I need to figure out what this distance is here. Okay, so if I subtract 90 from 150, I'll have this little slice in here, which is 60, which means that my purple slice in there is 30 degrees. So I can write 150 also as south 30 degrees to the east. Okay, and then for part B, northwest 50. So if this is 50, This is my west and this is my north. Probably should be putting arrows on these guys. What's the quickest way that I can figure out the distance from this north line all the way around here? Yeah, because this whole thing actually makes a full rotation here. So if I do 360 minus 50, I should actually get this leftover blue piece here. So it's 310. Okay, that won't always be the case depending on what your bearing is. You'll just have to decide. Maybe it's like 180 plus that amount or 180 minus that amount if we're measuring from the south line. Yeah. For A, so we had 150 here. So in order to get the 60, I just did 150 minus the 90 that's up here. And then this also has to add to 90. Because I need to know what this is from the south line toward the east. Okay, so remember guys, your quadrant bearings, they have to be between 0 and 90. They're always that acute angle depending on what quadrant you fall in. It can be southeast, southwest, northwest, northeast. Good? Any other questions? Okay.